Friends, first of all, I introduce myself. I am Dr. TYBSc, working as an associate professor at Mahatma Gandhi Vidya Mandir's Arts, Commerce and Science College, Manmar. Today, we are going to consider the PowerPoint presentation on nuclear chemistry. Nuclear chemistry is the optional paper for TYBSc special subject, chemistry. Third semester, according to the syllabus of nuclear chemistry, chapter 1st, atomic nucleus. This PowerPoint presentation is prepared on this chapter. Now, let's start this PowerPoint presentation. When we consider the concept of atom, since 3 years, FYBSc, SYBSc and now TYBSc, the concept of atom, when we consider in 11th and 12th, as atom consists two distinct regions. Inner region in which nucleus is situated. Nucleus is nothing but this is the dense mass centrally situated in which neutron and proton take place. Whatever electron is revolving around the nucleus in outer sphere. This outer region and inner region, when we consider both, the nucleus, which is called inner region, having radius 10 raised to minus 15 meter, whatever the outer space, outer orbitals, outer sphere having radius 10 raised to minus 10 meter. Inner sphere nucleus consists neutron and proton, whatever electron revolving around it. And we already considered the whole mass of atom centrally, it is nothing but it is the centrally situated dense mass of nucleus. That means the mass of neutron, proton and electron. Electron having a negligible mass 0.000555 atomic mass unit, hence it can be ignored. But when we consider the mass of atom is equal to the number of protons, sum of both number of proton plus number of neutron. And when we consider the mass number, we can subtract. When we consider the proton, we can subtract the neutron from mass number, we get proton, number of proton. And when we consider these subatomic particles, proton, neutron and electron situated in atom, nowadays in nuclear chemistry, instead of atom, we can say nuclide. And proton and neutron commonly called nucleons. Nucleus, that is the nucleus. Now, when we consider, rather than this, different subatomic particle in form of quark is also present in atom. Some of the quark which is identified, 17 quark total, 17 quark had been identified. Out of this, U type and T type is identified in inner sphere, in nucleus. Now, when we consider the characteristics of some of the subatomic particle, it is important here its symbol, location, charge and mass. Electron having symbol E, out which is present, which is located in outer sphere, having charge -1 and mass in atomic mass unit 0.000555. Proton having symbol P, which is located in nucleus, having charge +1, mass 1.0073, which is also located in inner sphere. Neutron having symbol N, which is present in nucleus, which having no charge but mass is dense, that is 1.0087 atomic mass unit. When we consider antiparticles, electron having antiparticle positron, proton having antiparticle antiproton, and neutron having antiparticle antineutron. This is about the particular subatomic particle. Now, when we consider the classification of nuclide, the classification of nuclide, when we consider, there are two. The nuclide are classified on the basis of number of proton and neutron, and other way which is based on their stability. When we consider the classification of nuclide on the basis of the number of proton and neutron, first one is isotope, which already considered since 12th science. These are the nuclei. Isotope means these are the nuclei which belong to same element, having same number of proton but different number of mass. The best example is hydrogen, 111, that is number of proton, 123, that is number of mass. Second example, sodium 2211, sodium 2311, and sodium 2411. That means in hydrogen, same number of proton 111 in hydrogen, deuterium and tritium, where mass number is respectively 1, 2 and 3. Similar manner, in case of sodium, mass number is 22, 23, 24, whatever number of proton is same, 11, 11 and 11. Now, second type, that is isobar. These are the nuclei of neighboring element, having same number of mass but different number of proton. That means atomic number is different. When we consider example of carbon 6, number of proton is 6, carbon 14, mass number is 14, number of neutron is 8, 6 plus 8 will get 14, and nitrogen, that is 14 its mass number and 7 is atomic number, that is number of proton. Ultimately 7 is number of neutron, 7 plus 7 is 14. And when we consider another example, that is sodium 2411, magnesium 2412, that means mass number is same in sodium and magnesium 24, but its atomic number is different, 11 and 12 respectively. Now next, third one, isotopes. These are the nuclei that contain the same number of same number of neutron. The nuclei, however, differ in the number of proton and also mass number. When we consider example, that is carbon 13, so nitrogen 14, sodium 23, magnesium 24, and atomic number, carbon 6, nitrogen 7, sodium 11, magnesium 12. Mass number and atomic number are different, but in all element, in all nuclide, the number of neutron is same, 7, 7, 12, 12. And hence, when we consider last type, that is isomer, these are the nuclei containing the same number of proton and neutron, and hence mass number is same. They, however, differ in their energies. The nucleus possessing the higher energy is usually radioactive and emits the excess energy in form of gamma radiation. The unstable radioactive nuclei is said to be metastable state and denoted by M, small m. Thus, the best example of isomer is cobalt 60 in metastable state, that is denoted by cobalt 60M and cobalt 60. Bromine 80, its mass number indicated by 80M and 80. Next, we already considered the nuclide are classified on the basis of number of neutron and proton. The four types which you already considered: isotope, isobar, isotone and isomer. Now, the classification of nuclide on the basis of stability which you have to consider. Stable nuclide, these are the nuclei that are permanently stable. The proton and neutron content of the nucleus remain unchanged permanently. That means number of neutron and proton cannot change. The stable nuclei may become unstable when it is bombarded by heavy energetic particle. That is, under surf condition, there are about 274 naturally occurring stable nuclide is there. When we consider example, oxygen 16, 17, 18, 35, 37, sorry, oxygen 16, 17, 18, whatever, chlorine 35, 37. These are the stable nuclei. But when we consider unstable nuclide, these are the nuclide which are unstable, continuously emits the radiation, possessing high energy, and due to continuous emission of radiation, its mass, the loss in mass take place. The number of proton and neutron content of this nuclei change spontaneously with time. Therefore, this nuclei get transformed into another one. The unstable nuclei are said to be radioactive. During the transformation of other nuclei, the number of proton and neutron of the old nucleus are either rearranged or some of them are ever lost. Both these processes are accompanied with the emission of radiation, which consists of alpha particle, beta particle and gamma rays. About 700 to 800 nuclides are unstable. This includes the naturally occurring radioactive nuclides also. Now, the next concept, an important concept of this chapter, that is binding energy. Let us consider a nucleus indicated by X. Affix A, capital A, indicates mass number. Suffix Z indicate number of proton. With atomic mass small m in atomic mass unit, this nucleus consists Z number of proton and A minus Z of neutron. We can calculate the theoretical mass of nuclide, that is X A Z is equal to Z MP plus A minus Z Mn. Here is Mp is mass of proton and Mn is mass of neutron, respectively. When we consider the difference between calculated mass and actual mass, which is called mass defect. This mass defect indicated by delta M, and which is small. When we consider the loss of mass during the neutron is accompanying with the loss of mass, neutron as well as proton, this loss in mass is called mass defect. It is the characteristics of nuclide under consideration. Now, binding energy means, what is binding energy? According to the Einstein principle, mass and energy both are interconversible. This means that when the mass is lost, the energies appear. The liberated energy in this process is mc square, where c is the velocity of light. And when we consider, according to the above principle, the liberated energy is given by the equation E is equal to delta M into c square in Earth. This equation means the formation of nucleus, that is nuclide X, from its constituent particle is accompanied with the liberation of energy. Let us now consider the reverse process. If one breaks the nucleus into the Z number of proton and A minus Z of neutron, the same energy E has to be supplied to the nucleus according to the principle of conservation of energy. The supplied energy is called binding energy. In very simple word, the binding energy is the energy that must be supplied to the nucleus so as to break it into its constituent particle. And we expect higher binding energy of the nucleus. This nucleus is more stable. When we consider the one atomic mass unit, the is equal to 1.661 into 10 to the minus 24 gram. Therefore, the energy is liberated according to the Einstein principle, that is 931 million electron volt, which is given in this slide. You see keenly, then we get. Therefore, one atomic mass unit of mass is equivalent to 931.1 million electron volt of energy. Since mass defect of nuclide X having mass number A and atomic number Z is delta M in its atomic mass unit, is obviously the energy required to break nuclide A into Z proton and A minus Z neutron, that is delta M into 931.1 million electron volt is equal to binding energy. This is the concept of binding energy, and in this chapter the question asks on binding energy for two mass, but the example of binding energy is asked for 4 mark. And hence, when we consider the calculation of binding energy and further average binding energy is equal to delta M into 931.1 MeV. Mean binding energy or average binding energy B bar is equal to binding energy upon mass number A. And hence, when we consider the example, here the example is given. The atomic weight of krypton having mass number 84, atomic number 38 is 83.9115 atomic mass unit. Calculate the mass defect and binding energy of average binding energy. Mass of proton is also given here, mass of neutron also given, and mass of krypton also given. Then it is very easy to find out the mass defect first, that is the subtraction of the expected mass and isotopic mass, then we get mass defect. Once we get mass defect, then binding energy is very easy, that is mass defect into 931.1 in million electron volt, we get binding energy. Then average binding energy is equal to binding energy upon mass number. In this example, the binding energy mass defect is 0.7689 atomic mass unit. Hence, the binding energy is equal to 0.7689 into 931.1, we get 715.9 MeV. And average binding energy 715.9 upon 84. 84 is the mass number. Hence, we get after division 8.52 million volt is the average binding energy. As per this, the example which you have to solve for homework purpose, which is provided along with the e-material. Now, for this chapter, it is sufficient now, and for your patience, thank you.